Hey guys, this is Patrick from STH, and this is the 4th generation Intel Xeon Scalable processor, codenamed Sapphire Rapids. And this is a $17,000 processor called the Intel Xeon Platinum 8490H. Now, the only thing crazier than having a $17,000 processor in your hand is having trays of $17,000 processors and a couple other ones that are also very expensive, because today we have the launch and we wanted to check out the high end of the SKU stack. Now, on the STH main site, we have a giant article that has over 10,000 words with all the details, diagrams, pictures, everything you need to know about Sapphire Rapids. But for this, we're gonna do something that's a little bit more fun and just talk through what are the new chips, how do they perform, how do they compare to AMD, what are some of the kind of quirks of the entire setup, because there are many to Sapphire Rapids. One example is that this $17,000 CPU does not have all of the features that you can get on the Xeon Scalable series. So with that, let's do a lightning round on Sapphire Rapids. About 2 months ago, AMD released the AMD EPYC 9004 Genoa series. This is a 9654, which is a 96 core part. Intel does not have anything that directly competes with this part in this generation, but what Intel does have is a SKU stack that kind of competes more broadly in the server market. Now, a lot of folks are gonna get hung up on the fact that Intel does not have a 96 core SKU. That's fine, that is what it is. We're gonna show you the performance numbers that, yeah, this thing is a beast compared to Sapphire Rapids, but at the same time, Intel has a much larger SKU stack that really covers more of the market, and I think that that makes sense because Intel is really going for volume here. Now, while folks really like to focus on that top end of the SKU stack, so 60 cores versus 96 cores, the fact of the matter is that most of the CPUs that are out there are really gonna be like 32 cores or something like that in this generation. And one of Intel's biggest markets for selling the Sapphire Rapids Xeons is actually, well, previous Xeon owners, right? The organizations that had things like, say, 1st generation Intel Xeon Scalable Skylakes and Broadwell EP, so those are the E5 V4 generation, for example, or even Cascade Lake or something like that. And even if you had a Skylake or Cascade Lake part, which was, by the way, the new part in the market up until 2021 when Ice Lake launched, well, those things topped out at 28 cores. So you couldn't even get a 32 core part at that point. And cores are great. We're gonna get into the SKU stack a little bit more, but there are other features that the new series has that we just never had before. For example, this new generation has DDR5, so you get 8 channels of DDR5, 4800 memory, and you can actually run it in 2 DIMM per channel mode, so you can see that we actually have a Supermicro 2U server here that has 2 CPUs and 32 DIMM slots, which is actually more than the AMD EPYC Genoa, so you have fewer memory channels, but because you can actually run 2 DPC, you can get 32 DIMMs in this, whereas Genoa right now, you can only put up to 24 DIMMs in. And DDR5 adds like 50% more memory bandwidth, but that's only the start of the advancements. For example, Sapphire Rapids adds a total of 80 PCIe Gen5 lanes per CPU. So not only do we get way more lanes, but we also get PCIe Gen5, which is way faster. Just to put that into perspective, each PCIe Gen5 by 16 slot that you get, and remember, you get up to 5 of them per CPU, has more bandwidth than all of the PCIe connectivity that you would have in a Skylake or Cascade Lake server on a single CPU. So that means that we're talking like over 5 times the PCIe bandwidth in a brand new 2023 CPU as we would have bought in January of 2021 in a Cascade Lake refresh CPU. I mean, that is absolutely crazy. And that PCIe Gen5 is only part of the puzzle because we also get CXL. Now, Intel originated the CXL spec, but has now become an industry-wide standard, and even see things like AMD adopting that. But the differences in CXL are actually super interesting. Now, both Sapphire Rapids and the AMD EPYC Genoa support CXL 1.1. And that is really the 1st generation of CXL, and it's gonna get way more exciting in the future. We have an entire video on CXL that if you wanna learn the basics, you can find that video linked in the description. But the AMD and Intel implementations of CXL are very different. For example, AMD is really focused on supporting CXL Type 3 devices. The CXL Type 3 devices are memory buffer devices, but they really just kind of think of them as like, you put memory on what looks like a PCIe card, because PCIe and CXL use the same kind of like physical lanes, and you basically get this by 16 card. This is the Astera Labs Leo platform, and there are a total of 4 DIMM slots in here. There are DDR5 DIMM slots, and if you plug this into a by 16 slot, you get a total of like what's effectively like 2 DDR5 memory channels that come out of it, or at least about that much bandwidth. But the other thing, of course, is the fact that I also got 4 more DIMM slots, and the latency between going to the card is pretty much like the latency of going to a remote socket in a normal server. So if like you're this CPU trying to get to memory that's on this socket, packet, it's about the same latency as going to something like this. But that's also where this starts to get a little bit weird, because while AMD is really focused on Type 3 devices, Intel is focused on supporting Type 1 and Type 2 devices, which means that technically this memory expansion device does not work on or is not supported on a Sapphire Rapids platform. And you might think like, okay, why is that such a big deal? Guys, we've literally seen at like shows since Supercomputing 2021, we have seen demos of these like kind of memory expansion devices on all of the different, Intel development platforms. This is like literally 2021. So it's been like over like a year that we've been seeing just the entire industry develop their memory expansion devices on Intel platforms, yet they're not supported in this generation technically. My sense is that we're probably going to see some support as the Emmitsburg platform kind of gets a little bit more mature and stuff like that. So I think that that's something that is going to change over time, because Intel has a pretty high standard for really supporting stuff. Speaking of high standards, when I was up at Intel for the workshop, before this gets launched, one of the cool things I got to do is actually go and tour the data center facility that Intel uses, and they have thousands or tens of thousands of processors set up of different generations. So not just Sapphire, but some of the, like Emerald or Granite or whatever are all there. And they have these like rigs set up where they can do things like change like specifically voltage regulators and all kinds of stuff. And they have all this like telemetry and control over the systems. So that way they can go do things like create failures and like figure out like where things fail. So it's like this giant like reliability lab that I got to go tour, and it was just kind of super cool to get to go see. The reason that Intel does that is because Intel's focus is like saying, hey, look, if we're going to release a product, we're going to have like super high quality. We're not going to have bugs. We don't want like cores to fail in the field, which actually does happen if you're like operating at like a hyperscale, like a Facebook, Microsoft, Google, like that kind of scale. And so that is really their focus in this generation. I just thought, man, that was just super cool. And so, when we say that we don't have like CXL 1.1 support with these Type 3 devices, my sense is it's like maybe they haven't gotten to that level of testing yet. Because let's face it, all of the CXL primitives are supported by the chip. So it kind of feels like we should be able to support a Type 3 device. Now, 50% more cores, DDR5, PCIe Gen5, CXL. I mean, those are all super exciting, but there's more to this actually, which is really the acceleration story. Now, a lot of the coverage that you're going to see that's going to come out today is really going to be about accelerators. And there are really two types of accelerators, and this is a really important concept to kind of keep straight as you're kind of going through those materials. The two different types of accelerators are, there's kind of like the ones that are like on die and like, really are like instructions or like data paths on the actual like core themselves. And so those are things like AVX 512. A new one for this generation is called AMX, which is an AI. So if you're doing like AI inferencing, you get a pretty huge speed up actually using Intel AMX versus the older generation VNNI. And those are features that are really built into the cores themselves. And so those are not external devices. You just have to have software that supports them. The instructions fire up and you're ready to go. Intel has put a lot of effort into having things like that AMX actually work with TensorFlow out of the box. So you don't have to go do a lot of work to be able to get good AI inference, or at least better AI inference performance on your CPU. But then there are four main accelerators really that are in the Sapphire Rapids generation that are actually like kind of like hardware accelerators that are super cool. Now there's one of those four accelerators that is in, I think, every single SKU that you have, and that is a DSA. Intel DSA helps with data movement, and that's the one I think a lot of people are excited about because it's on everything, and things like SPDK, DPDK, like those kind of things that are really meant to go offload and like move data around systems a lot faster. That's what that accelerator is designed for. Quick Assist, or you see it abbreviated as QAT, is something that we've covered a number of times on STH. We've done things like, have Quick Assist cards, and we've shown it in like the Xeon D. We have videos on that. We'll link those in the description. And we've even done a hands-on preview where we actually tested the Quick Assist acceleration, also the AMX acceleration, a couple months ago. Quick Assist is used for things like crypto and compression, offload, and acceleration. And those things are actually now hardware accelerators that are built into the CPU dies themselves. And so you can get, if you have them and you use them, you can get a lot more performance for things like, if you have an HTTPS web server, just doing the TLS handshakes or doing compression, which, everything does compression these days, right? And so that's a really cool feature that you have in the Sapphire Rapids generation. There's also the Intel Dynamic Load Balancer, or DLB, which is for things like VPP and IPsec and stuff like that. It's kind of, those are really the applications there. The other one is the Intel Intel in-memory analytics accelerator. And that one is designed to accelerate some of the transactions that happen when you have like these big in-memory databases. And so that's what that's there for. Now we've already covered that Intel has more cores. They have DDR5, PCIe Gen5, CXL, accelerators. But the other big one that is kind of like an accelerator in some ways is that they do have a new series, which is the Xeon Max series, which you can see the little Xeon Max pillow back there that I stole from Supercomputing 22. But that Xeon Max series has 64 gigabytes of HBM2E memory on board. Now you can actually use that memory and you could boot the system without any DDR5 in it, just using that 64 gigabytes of memory per socket. You can also run it as its own memory kind of pool. So you have a faster high bandwidth memory pool, and then you have a larger DDR5 pool that kind of backs it. And the other one that you can do is you can actually have caching mode. So it's a transparent mode where you have the ability to cache the DDR5 like hot data in HBM close to the CPU. And a lot of times you get a lot of performance out of that. We actually saw that back when we did the Xeon Phi Knights Landing system a long time ago. I think I had the system and then Linus got my system, but it's pretty similar to what the Xeon Phi was back in that generation. It's just updated with new technologies like HBM. So I mentioned earlier the fact that there are $17,000 CPUs in this generation. That is a Platinum 8490H. And that H tells us that this isn't just a normal processor. That processor can scale. So not only does Intel have single socket and dual socket servers, but they can support up to 4 and 8 socket servers. Something that we'll be launching today also will be the fact that I did the Supermicro introduction to their X13 line. And in one of those videos, we actually showed off a 8 socket Supermicro 8-way server. I mean, that was like super cool to go see and actually get to go play with it a little bit while we were there just filming. The previous generation of Ice Lake servers could only do 2 sockets, but there was a Cooper Lake variant that only went up to 28 cores, and that one could do 4 and 8 socket, and it was really made basically for Facebook. Let's call that what it is. But you know, that was really the previous generation. So this is by far, in over 5 years, this is, and probably I would say even more than that, this is the biggest 4 socket, 8 socket server CPU release, clearly. And then also, I think this is the biggest Intel release, just when you look at all of these different things that went into it. I think this is the biggest release in over a decade for Intel. But yeah, I think it's about time. Let's talk about the SKU stack, because although we talked about the $17,000 on the high end, at the low end, it's just over $400 for the cheapest SKU, which is a Xeon Bronze processor. So Intel gave us this table, which was pretty hard to read, pretty hard to compare. And so what I actually did was I kind of made a kind of color-coded and data barred, just kind of made a version of this that we can go take a look at. And just, I want to talk about some of the insights that this little activity helped with. I'm sure that there's typos, because sometimes there's typos in the early sheets that Intel gives us. Also, then, we transcribe it, and sometimes there are little typos there. So I apologize if there are any typos, but hopefully we've got everything right. Okay, so parsing this out, some of the things that you're going to notice. One, there's only a couple of Xeon Max SKUs. I think there's like 5 Xeon Max SKUs, and those are the ones with the HBM memory. So those are always a little bit different because you have 64 gigs of HBM memory on board, and that costs a lot to actually go put that on. That's like hard cost that Intel has to go procure that HBM2E memory, put it onto the thing. I mean, that is a not cheap process to go do Xeon Max, right? So those are always kind of like in their own little separate category. But then when we look at all of the CPUs, just one of the interesting things I thought was the fact that the most common just CPU core count in the entire setup was actually 14 of the SKUs are actually 32 cores out of like 52. So 32 cores is clearly a targeted like SKU level or core count for Intel in this generation. Now the average cost per core for Intel is like $146 if you include those Max SKUs. If you exclude the Max SKUs, I think it's like $137.48 or something like that. Since I know folks are gonna wanna know the comparison to AMD, AMD is $119 per core, and even at the top end, so that AMD EPYC 9654 that I showed you, the 96 core SKU, that's only $123 per core. So Intel is definitely pricing its products at a premium to AMD on a per core basis. Now, of course, cores are not everything, because you want to know really how much work you can get done with a given processor. So clock speed is also kind of important. And when we look at the base clock and we take, cores times base clock, and then we, figure out how much it costs to get a like 1 gigahertz on one core like worth of performance, well, that's actually kind of an interesting number just to compare as well. Intel averages just over $64 per core gigahertz. And if you take out the Max series, that gets to just under $60. AMD, by the way, is just under $40 per, so it's actually a pretty huge premium when we get away from cores. We actually look for like cores times clocks. Actually, at base clocks, AMD's premium is much smaller than Intel's, I guess. And part of that is because AMD's average base clock is like 3 gigahertz, whereas Intel's average base clock is something like 2.3 gigahertz. And even if we were to go and take a look at the all-core turbo numbers for Intel, if you do that and you take like the the cores times the all-core turbo frequencies and like kind of figure out what that cost per gigahertz is, you're at just over $48 for Intel, including the Macs, and just over $44 without it, which means you get a 10 to maybe 20% premium for the Intel parts, even at their all-core turbo versus the base clocks and AMD's pricing. Now, part of that is really due to the onboard acceleration that I spoke of earlier, and we showed a little bit of the performance of. Now, there are two kinds of accelerators. There's the accelerators that are in absolutely every platform, and those are things like AMX that are actually built into the cores themselves. But then Intel actually has acceleration blocks on the SKUs, and if you look at those, you'll see that Intel has like 4 main accelerators: DSA, QAT, DLB, and IAA. And of those, DSA is the only one that's on every single SKU. However, only 27% of the Intel SKUs have all 4 DSAs that are like maximum if you have like the big XCC die. Well, 73% only have 1 DSA. On the QAT side, well, like 56% of the SKUs don't have a QAT accelerator, 56% don't have the DLB accelerator, and around 60% don't have the IAA accelerator. So when Intel goes and they have all of their things, and you're gonna see this a lot in the, some of the tech press that just takes like the Intel slides and stuff. When Intel talks about like, hey, we have great acceleration and it's like amazing and all that kind of stuff, it is. Let's be very clear. However, you have to also remember that more than half of the accelerators that are like built in or could be built into the things, more than half of the SKUs literally don't have any of them turned on. And part of that is really because of Intel on demand. So Intel is what they're kind of dealing with, and I kind of can see both sides of this. I think they're getting a lot of people are just like bashing them in places like Reddit and forums and stuff like that. But what Intel on demand is really interesting, right? Because so now think about what Intel has. Intel has a variety of SKUs, and now you have different levels of acceleration. And if you want to go and make different levels of acceleration, cost different amounts, right? Because you're getting more value because there's just so much faster when you can actually use the accelerators. Well, then what you need is a way to go make SKUs. And you don't want to have like different SKUs if you have like 4 or if you have 0 or like 2 or 1 or something like that of the accelerators that are active, like doing that, plus all the core counts, clock frequencies, cache configurations, do you have HBM or not, all that kind of stuff. Like there's so many different configurations that even just getting down to like 50 something SKUs is pretty hard for Intel right now. So their idea with on-demand is they can ship the SKUs, and then if a OEM wants to, the OEM, call like Lenovo, Supermicro, those kinds of companies, they can go and they can actually turn on those features for customers. And by the way, companies like Lenovo have been doing this with cores and stuff like that for a long time, like many years now. And so that's something that may shock people, but on the other hand, it's also something that is pretty common actually for Lenovo, and also HPE and Dell are looking at this, right? Because with like things like Apex and GreenLake, they're of course looking at these kind of things too. And what the other thing that it gives you is the ability to go buy a processor today, and then later if you realize like, hey, I need DLB in this like cluster or whatever, I need QAT or whatever, you can then go and say, hey, Lenovo servers, I need more performance. Can you get me those accelerators? And there's the option to go turn them on permanently, or you could potentially just turn them on, for a period of time, I guess, with on-demand in the future. And so I don't know if that's implemented yet, but that's kind of where the vision is. But the flip side to it, I totally get, guys. Like to me, like the acceleration that's built into these things, we're going to show an example of this later, but the acceleration that's built into Sapphire Rapids is absolutely the thing that turns it from like AMD and Intel competing to Intel can actually just kind of blow away some of the AMD parts, right? Even at lower power consumption, all that kind of stuff. So you have like your main competitive advantage, but then for over half the SKUs, you don't even turn it on. And that just kind of, I don't know, just to me, it feels like that's one that I think that this was something that Intel decided to go do when they had, like 97, 99% market share and said, okay, we're gonna go do this. All the OEMs bought into it. And remember, the OEMs have to actually go develop the systems to go do that, right? So they're like, hey, Intel, we spent all the money on development. When do we actually get to turn it on and monetize it? And so I kind of get that total chain. But on the other hand, it's like the main competitive aspect to Sapphire Rapids and Intel's putting it behind a paywall, right? Which also means though that the prices per SKU that we saw and all that kind of stuff, they're priced already at a premium to AMD, and most of the SKUs that are priced at a premium don't even have that acceleration. I would love to hear your thoughts on that. Comments down below. I know a lot of people are gonna have thoughts because I'm pretty mixed on it as well. Okay, so let's get to the processors themselves. What the first thing we want to talk about is the cores. They're actually the P cores, so they're Golden Cove cores, something that folks have seen kind of variations of in like desktop parts and stuff like that. And with the server generation, there are a couple things that you definitely get, which are nice. First off, you get more level 2 cache. You go from 1.25 megabytes up to 2 megabytes, which is really good because Intel, frankly, just needs more cache in its architecture at this point. It's just, it's taking a little while to get there. And the L3 cache has moved from 1.5 megabytes per core to 1.875 megabytes per core, but there are parts like out there and in the SKU stack because Intel can turn on or keep the cache on even if the core that's next to it is disabled. That means that Intel can actually get something like I think there are parts like over 2.8 megabytes of level 2 cache or level 3 cache per core. So 1.875 see that kind of like as a minimum. Now, as we've shown Sapphire Rapids, for over a year on STH, something that you've probably seen is like there's like this 4-tile die, and that's called the XCC die. You may have noticed that on our SKU stack. The XCC die takes 4 compute tiles. Each compute tile has 15 cores plus 1 acceleration block. There are also things like the UPI links, which are upgraded in this generation, as well as the PCIe links, and 2 memory controllers per compute tile as well. There's a variation of this XCC part, which is the HBM part. That HBM part, that's the one where you get those 4 16 gigabyte HBM2E packages. So each compute tile gets its own 16 gigabyte HBM2E package, and that's how that is configured. In high performance computing applications, a very common thing to do is do something like an MPS equals 4, where you basically split up your CPU into 4 different quadrants. And if you did that on this, you would have access to up to 14 cores. There's actually no 60-core HBM Max part right now, but then you also get the HBM memory as well as 2 DDR5 channels for each compute tile. And that's really done just to localize all of the memory access and transactions. The other die that Intel really didn't talk too much about before the launch is the MCC die. Now, the MCC die has a total of 34 physical cores. However, for yield purposes, it has a maximum of 32 cores, which means that really this is the die that is focused on those kind of lower cost, lower power applications. We mentioned this earlier, but the TDP distribution, like Intel has more SKUs that are under 200 watts than AMD EPYC has SKUs in total. And by the way, the lowest TDP on an AMD EPYC 9004 Genoa part is now 200 watts. So there's like an entire range of Intel Xeon Sapphire Rapids processors with this MCC die or MCC package that are actually lower power than anything you can get on the AMD side. Just something to keep in mind. And here's a quick just table of the die package details if you want to see that. There are some interesting points to the memory and platform that I think we should cover real quick. First off is Intel Optane DC Persistent Memory, or PMem 300. This is called CrowPath, and one of the interesting things there is that actually there was a generation of Optane, even though Optane people have probably heard by now that it's been canceled, but there was actually a new generation that was designed for Sapphire Rapids. It was tested in Sapphire Rapids and ready to go. This is a new, faster generation, and you can do things like all 3 modes, where you can have the memory mode, the storage mode, or the mixed mode. Beyond that, this generation runs a lot faster. It runs at DDR5 4400 speeds. So it is a little bit slower than the maximum that you can get at DDR5 4800 on the DDR5 SKUs, but at the same time, it's actually a lot faster than the DDR4 generation of PMem. Now, if you want to learn more about DC persistent memory, go look for our glorious complexity video that kind of go through all of the kind of weird things to DC PMem, because it's definitely kind of fun technology. And really the reason a dead product line is being introduced now is because this is really the last generation. Intel has customers that it needs to kind of fulfill requirements to or commitments to. So it's kind of made all these things and it said, okay, we're gonna go build you out this generation and we'll support you through this generation, but we're not expecting any future generations. Now, one other little interesting thing on the platform side is that we do get the 80 PCIe Gen5 lanes per package. And that doesn't matter if you have the XCC or the MCC package, you're still gonna get 80 lanes, and that's by 16, so 5 by 16 PCIe Gen5 blocks or routes. One interesting thing though is that you can actually run those routes. You can run them, of course, in PCIe Gen5 by 16, by 2 by 8, 4 by 4. But if you want to get down to by 2 bifurcation, well, that means you actually have to go down to PCIe Gen4 speeds. You can't do it at PCIe Gen5 speeds. I didn't believe it, and then I got the information that that's actually the case. And so that's a little thing about the Intel platform that I think most people, a lot of people are asking, like, why don't we just do PCIe Gen5 by 2 drives? And one of the big reasons that we're probably not going to see that in this generation is just the fact that Sapphire Rapids does not support PCIe Gen5 by 2. So, that's like half the servers out out there aren't going to support it, which means the drive manufacturers are most likely not going to support it. Okay, so let's get to performance real quick. We're just going to zoom through this just because these are just charts, right? The big thing though that we saw on a lot of these things, like for example our Linux kernel compile benchmark and a lot of other ones, is the fact that we definitely got a huge performance uplift from this, right? Just going from 40 cores up to 60 cores, it's 50% more cores. You get all the new microarchitecture benefits, and of course, even not using accelerators, you get a massive jump in performance compared to the previous gen. And if you're on something like a Skylake or Cascade Lake, you're going to see a huge increase. Literally, we have things like the Quad Xeon Platinum 8380H is on there, which is like the Cooper Lake generation, and you can literally get more performance than you got in 4 processors in just 2. And that is exactly what Intel is saying, like, hey customers, this is why this is such a cool platform. Things like C-Ray are pretty similar to like a Cinebench on the Windows side, and there AMD, just because of their cache structures, tend to always have a little bit of a benefit, and so you see that they tend to be faster here. The 7-zip test is actually struggling a bit with just the higher core count CPUs, and that just kind of brings us to a really good point, which is just the fact that if you have a 60 core or 96 core or whatever CPU, very few of those are actually going to run like single workloads at a time. Most of the processors these days are going to be virtualized, or they're going to be running containers or something like that. If you look at the clouds and a lot of people in virtualization stuff, most people that run virtualization clusters say like a huge portion of their VMs are like 8 vCPUs or less. And so at this point, when you have 120 threads on a single processor, like of course things are not going to just scale out there. One of the things that you actually notice on a lot of these benchmarks, or some of the benchmarks that we have, is that they're not able to take advantage of the full core counts. And so you see that you hit a single threaded workload or portion of the workload, and then you're at like 99% idle, and you got that like one thread that's running, and it looks silly these days. One of the fun ones that we did was we actually ran our STH Nginx. We ran the workload traffic pattern from an old version of the STH website. We just kind of ran and just saw like, hey, what does that web server look like? And you definitely saw some really big performance improvements with this new generation, because you have more cores, but you also have things like DDR5 memory. We have a MariaDB pricing analytics workload, which is literally for a large, very, very large storage OEM, figuring out how to go do pricing dynamically and do like kind of deal pricing and all that kind of stuff on any kind of BOM that they would ever put out based on region and all kinds of stuff like that. I mean, this is a absolutely crazy application that you probably do with AI these days, but it's a like real business intelligence thing that actually was implemented in Oracle back in the day at a very large storage vendor. So I just kind of want to, we're using sanitized data, but this is a very real world use case here. And there, what you notice is that you do get very good performance. However, this is one of the workloads where kind of like this dark horse of the AMD EPYC Milan X, where you have that higher cache, you actually get a huge performance benefit to more cache. And we don't have the Xeon Max series, so we can't really do that comparison on this workload. My guess is that it would actually perform extremely well here, just because the dataset size is over 768 megabytes. But at the same time, it does kind of bring out the importance of having things like, faster and closer caches. Now, when we get to the virtualization side, of course, we are going to see some benefits. And there, these charts actually get a little distorted by the fact that we have that 96 core CPU out there. If you look at the larger VM sizes, those tend to be mostly kind of just really bounded by the amount or total system memory. It's really the smaller, like the medium and small sizes, that you start to see some of the differences based on the CPU performance. So if we zoom in and we go look at the medium size, you're going to see pretty just massive virtualization gains versus, especially if you have a Skylake or Cascade Lake system, you're going to see massive gains in this generation. And at this point, you might be wondering what the heck is going on between this whole Xeon Platinum 8490H and the AMD EPYC 9554. Because you might be saying like, hey, 60, 64 cores, Intel AMD, they should be pretty close, 350, 360 watt TDP, like they should be close, right? Well, a couple things to keep in mind. The AMD EPYC 9554 has 4 more cores. So you get like 6.7% more cores, right, just based on that. But the other thing is that AMD with Genoa, they didn't just increase core counts, they also increased clock speeds quite a bit. So the EPYC 9554 has a 3.1 gigahertz base clock. The base clock on the Intel 8490H is only 1.9 gigahertz. And the all-core turbo on that is only 2.9 gigahertz. So even at all-core turbo levels, they're not even reaching the base clocks on the 8490H that AMD has like on the base clock on the 9554. And since IPC has gotten a lot closer between the two of them, the fact that you just get way more clocks and you get more cores, well, that means that AMD is most likely going to be faster in a lot of workloads. And especially things where you have like an SLA or something like that, where you can get higher clock speeds, also allows you to have lower latency, and so that helps in a lot of those workloads. The AMD EPYC 9554 also is running at a 10 watt higher TDP. We didn't run this thing all the way up at 400 watts, but you can get another like 3% or so performance if you go run them at 400 watts, but not all servers will support that 400 watt operation. The other thing to remember though is just the memory side. The AMD EPYC 9554 has 12 DDR5 4800 memory channels, where Sapphire Rapids only has 8, so that's 50% more memory bandwidth just from that. And AMD still has a lot of level 3 cache on the chip, so it's not actually going out and doing those memory transactions as much as you might think. So while on paper you might say, well, AMD has 64 cores, Intel has 60 cores, they should be a lot closer. When we actually ran the systems, they were not as close as you would have thought, and that's really just kind of based on all of those factors combined. But that really brings us to the real story of Sapphire Rapids, which is that acceleration. Intel had a interesting but not incorrect, just a little slide about the fact that customer workloads differ from spec workloads. Spec CPU 2017 and spec int rate, that's definitely like the de facto standard for like the number of RFPs that use that still are just amazing. But what that's really designed to do is very efficiently scale out a single kind of workload across many cores. And what that practically means is that it scales super well, but it's also not testing various aspects of a CPU and memory and like system and stuff like that. It's really just kind of like seeing how fast you can go on a bunch of cores. Now, when you get to real workloads, take something like a website where you may have a database backend, you have a web front end, you're probably doing some kind of like proxy or something like that in there, and you're probably running some kind of interpreted language or whatever as well. I mean, there's all kinds of things that you're probably doing in a chain there, and maybe you're even doing some AI inferencing these days. Who the heck knows? So what Intel's basically saying is that hey, cool that they're spec, but because we're maybe not going to do so great in spec, what we're really doing is designing for customer needs, and that's what that really is right there. But that really gets down to acceleration. And the fact is, when we looked at the accelerators, we did an entire piece on this that we're going to link, but frankly, you get a lot more performance by using the Sapphire. You get a ton more performance just by using the Sapphire accelerators. And why that's really important is that, we really did this with like the 60 core CPUs, but if you get down to like say a 32 core CPU because you want to fit in a VMware licensing model, well, that's a really good case of where you want to have maximum per core performance. And so a 32 core CPU is still 32 cores, even if you have a full set of accelerators that are enabled on it. And so when we talk about things like being able to offload compression, being able to offload cryptography, being able to offload other like data movement and things like that, and freeing up a core or 4 cores or 8 cores or more just by having those accelerators, well, if you are now spending the same amount for that 32 core license, but you don't have to use those cores to go do all those kind of other activities, that is definitely a good case of where you can see that those accelerators have a lot of value. And that's also why I really wish that Intel just said, hey, with this generation, let's just go turn on all the accelerators, because I think that would make their case or their performance versus AMD Genoa a lot stronger. In fact, what we did was we literally took like an old STH snapshots, and we kind of set up a somewhat like the website would be set up, where we don't have things like backups running and all that replication, all that kind of stuff. And what you see is that if you don't have the QAT acceleration, that the EPYC Genoa is faster, but if you are able to go turn on the QAT acceleration, even though it's only a portion of that workload, you actually get so much more performance that Intel takes the lead at 32 cores. And so that's a good example of why I think that really having these accelerators often skews in this generation is, that's why I'm not like overly excited about on-demand. I think that Intel actually needs these accelerators on to have a really strong competitive story. The other thing on the accelerators though is the fact that if you kind of need a couple things, right, for accelerators to work. You need to have a roadmap that tells people, hey, every generation in the future, you're going to have these accelerators. Intel still hasn't provided that yet. And so that makes people wary, because there's like, hey, maybe you have it in chip this time, but like maybe next time it's not on the chip. And so if it's not, like, do I want to support it? And Intel's looking at it like, hey, if people don't use it, then I'm not going to go put it in future chips. And so you can kind of see how there's like that tension there. So if Intel doesn't just say like, hey, QAT is going to be in everything, start using this accelerator, then just it kind of like it kind of really hurts adoption. Another thing that hurts adoption is if like more than half of the SKUs don't have the QAT accelerator as a good example because, like if you're a software developer and you know that it's only an Intel technology, and if you have an Intel processor, there's less than a 50% chance that a SKU has the QAT acceleration even. I mean, like, are you going to develop for it even? And I think that that's, like, to me, one of the big things that Intel really needs to fix. Now, when we talk about power consumption, something that was nice was the fact that we definitely got lower power consumption on these parts. We definitely saw that the dual socket server, like this one over here, you would get a little under 1 kilowatt. We got a little over 1 kilowatt when we looked at the Asus AMD EPYC Genoa server just recently. And so, you kind of can see that if you're kind of planning just based on kilowatts, it is nice the fact that these are a little bit lower. Of course, you can go over a kilowatt if you start adding accelerators and NICs and all kinds of stuff like that that use a lot of power. On the single socket side, we also had a Supermicro server that was single socket, and that one actually was well under 500 watts, which was really nice to see. And just the fact that you can get a single socket server that has a lot of PCIe connectivity, has CXL, has all those kind of features, and is running at that power level, I think is awesome. Intel, by the way, has a much better single socket solution in this generation because they have 80 PCIe Gen5 lanes rather than the previous generations where they just didn't have as many PCIe lanes. Okay, let's kind of summarize this and kind of make it easy for folks. Sapphire Rapids is a massive jump over the previous generation of Ice Lake. So the third generation to fourth generation is a huge jump. You get DDR5, PCIe Gen5, CXL. You get built-in accelerators both on the cores as well as dedicated accelerators on some SKUs. You also can have things like Sapphire Rapids can have the HBM for the Xeon Max series. So it's not just talking about a maximum of 60 cores. It's also talking about the fact that the platforms are way, way more robust than the previous generation. And the impact of that is that you're going to see a greater than 2-to-1 consolidation ratio. If you're going from like a Skylake, Cascade Lake, so like first or second gen Xeon Scalable to a fourth generation, like that's a pretty normal upgrade cycle that we're in right now. And you're going to see massive gains where you can do like 2-to-1 consolidation, which is great. I think that the acceleration story that Intel has is awesome when they're enabled, but I also kind of wish that Intel just enabled all the accelerators and just didn't do this on-demand thing, because I think that that's a really strong way for Intel to, number one, beat AMD on a per core performance basis in this generation, but two, and also really importantly, just kind of get folks to use their acceleration technology so that way folks stay on Intel processors, right? Because, I definitely see the benefits of, in terms of like power consumption, in terms of using fewer cores or more efficient use of resources of using accelerators. I just wish that, we had more access to it. Now, I opened this piece talking about the $17,000 CPU that's designed for 4-socket, 8-socket, all that kind of stuff. And just frankly, guys, that is definitely a price that is seems to be there to be discounted, right? So just remember that street prices versus list prices are not the same. It's not like if you go buy a consumer CPU where the list price is most likely what you're paying. When these things go into servers, they're sold at discounts and stuff like that. So just remember that when we talk about the pricing. However, I do think that Intel does need to discount because if you just kind of look at their list prices compared to AMD list prices, AMD's list prices for things like cores and stuff like that are much lower. With that, if you want to learn more, go check out the STH main site. We have a ton of content there and much more in depth than we were able to go through in this video. And of course, on the STH main site, we're also going to have a lot more reviews and stuff like that of different servers. With that, thanks for watching and have an awesome day.